Amazing.
Yeah, thank you very much. Because everybody knows how to read, but it's work in progress. I'll value any obviously any comment. Help in some ideas. I guess yes, there is someone on the Zoom. Yes, yeah, so I'm speaking English now.
We have viewers on YouTube after the show.
Yeah, after the show. I have to speak.
About 15-20 viewers per video. Some of them are me checking that the video works. But...
Correct. So what is it about? The early days of evolutionary dynamics, people considered the replicator dynamics. Lots of references. One of the earliest ones is Taylor and Juncker, I think. The underlying assumption is that, in a sense, there is a constant environment. In short, there might be some noise coming from the fact that you have a finite population and looking at some continuous limit. But otherwise than that, the environment is fixed. So you can imagine of some sort of setup here, living in a petri dish, and everything is fixed and it just grows. However, in biological, ecological, settings, you actually need something else. You need some changing or varying environments. So you can imagine, for example, in the case of replicator dynamics, later on, I will probably speak of other dynamics, or just mention them. You can think of that petri dish. Now, the temperature will change. The temperature will change, the growth will change as well. And we'd like to know what will happen. I was actually quite surprised with not so many results out there. And most of the works are from recent years, mainly done in the future. Okay. And the example that I'm going to cover now, and speaking of other environment takers, is switching between environments. You're not going to have a gradual change, you're going to have a switch change. So, for example, in economics, you can think of changing in certain regulations, right? This will be your environment. Let's think about how to model it. So I'll present a very, very simple model. You can generalize it. You can think of a system of differential equations. Okay, so a system of differential equations. So we have a system for each state. You have, for example, two states. So let's think of two states. We have state one. This is the common thing that I will have. And then you'll have a state two. State one, state zero and state one. Let's call them state zero and state one. And in each state, you're going to have a certain replicator dynamics. Okay, so you're going to have a replicator dynamics for this state, x1, say, x1 dot equals to f1 of x. Suppose that this is the replicator dynamic. Later on, I will write it a bit more explicitly. And you'll also have the order. Let's keep my apps in order. So the x0 equals f0 of x. This will be our system, and we need to know how to move between states, right? That will give us the dynamical system. So for this state, for state zero, this is the high temperature or low temperature or something like that. For this state, I'm going to have this dynamics. And if I move from here to here, or from here to there, I need to tell you how it's done. So this is going to be done by a Markov jump test. I'm going to have some exponential arrival time. I'm going to jump between the processes. This is going to be the moment.
So can I think about seasons of the year?
So for example, you can think of seasons of the year. You can think of, as I said, temperature change, but season of the year is a bit more like, so for example, if, it's like Harry Potter, the snow ends and immediately you have a beautiful sky, that's the change you're thinking of. You want to have gems. Yeah, you want to have gems. But later on, we can think of yes.
But I can't think about, let's say, global warming, because this is a
yes, exactly. One of the possible directions that I will have at the end will be something like that. Okay, so So this is what I have here. And obviously you get a markup process. Okay, so there are, since two markup processes here combined, one is deterministic, and the other one is this changing in the environment. Together, they make a markup process, and it may have a stationary distribution, not necessarily. So it's a continuous time process. There are all kinds of questions of what's going to happen here.
Just can you remind me? So you think about the dynamics. So x dot is the derivative.
Yeah, it's a derivative. Okay, so I'll introduce some notation so we'll understand what we're talking about. So when I say x dot, I mean a time derivative. So this is the usual notation.
Like the
Population change. So x is how many people or the rate, the proportion of people using a certain strategy. So we'll have a certain strategy space. S is not a very good. So let's think of action. You will have a set of actions, right? And you will have a distribution x, which is a distribution over actions. And you actually want to know what is the statistics of the population. So that's what we. So usually, some initial example will have a replicator dynamics in a second one. So what I'm going to essentially think about, so evolutionary game theory started with ESS, right? Started with certain equilibrium. We didn't have dynamics. And people thought about convergence to ESS. But more generally, the dynamics, sometimes it does depend only on equilibria, but you want to understand the dynamics in general, right? Not necessarily that we're going to converge into a certain equilibrium. It could be that we're going to wander around the space. So usually you're interested in phase space. Occasionally, we'll have convergence to equilibrium. So I think that the proper generalization, in my case, would be the stationary distribution of this market chain. And also, if you think about it, suppose that you have just one state. Suppose that now you have only one state, and you have a certain equilibrium. And you begin from you start your initial state, your initial state. Your initial condition is very, very close to that equilibrium. It's an ESS, it's replicator dynamics. You're going to converge to it. So essentially, you're going to be in its neighborhood with probability 1. So the stationary distribution in that case is going to be just delta of this point. Just going to be a point mass here. Right? So in some sense, stationary distribution is the right notion, I think, to examine here. And I would essentially be considering the case where I can limit that to cases where you're interested in equilibrium. So very, very simple systems, which you don't have limit cycles or all kinds of chaotic behavior and so on. So this will be my main elements. Any questions? I'm not worried. You will answer. Okay, so I'm going to call it example 1-1. Right, because it's going to be my first example. Later on, you understand why 1. So first of the first. Yeah, complication. Okay, so let's consider two environments. I'm going to consider the most simple environment ever. Two seasons. One of them, there is a certain strategy that is going to be very, very, very good. One, any other combination is going to be very, very, very bad.
What is the interpretation of two players?
So it's a symmetric game.
Two types of populations.
There is only one population. Repeat the track. You have a strategy and a strategy. When we both play against each other, we have the same strategy here. We're going to get 2. Okay. And all the other cases are used. This is what we're going to have.
So randomly, randomly I meet some
other person with according to the statistics. the frequencies.
Repeat or continuous time?
Continuous time, continuous time. Everything here is continuous time. I'm from that region of space. Okay. Okay. So as I said, there is a transition between the state. The rates, the exponential rates, are going to be denoted by gamma. I don't know how to do a lambda in PowerPoint. So this is y, and you're going to have evolutionary dynamics, which is described here. There should have been an S here, x dot of S, right? So the change in S is going to be a replicator dynamics. So for those of you who don't recognize that, think that you subtract this from this. This is a different type of replicator. I think that this was actually the initial one that people started from with the top of relative growth and the logarithm of this.
Slash lambda space.
What?
Slash lambda space.
Slash lambda space? Okay. Right. So, and the reason I'm using this, main reason I'm using this is that for this example, I can actually give you a very, very simple description of this analytically. Right? Later on, we'll think about it geometrically, but now I think of it analytically. What I'm going to have here, two differential equations. So when you multiply this matrix by a vector x1 minus x, so if I'll do the calculations. Okay, so I think that the first example is important because then you'll have it in mind and everything will be easy. So
You can turn on the light.
oh, there is a light here.
That's very sophisticated.
Amazing. High tech nation, yes. Startup nation. High tech nation. Anyway, so if I take 2 0, 0, 0, and I multiply it by x1 minus x, right, I'll get 2x 0, right? And when I multiply it again from here, from the right, right, this is the average payoff for the population. I'm going to get 2x squared. So the ratio that we're going to have here between this and this is going to be 2x over 2x squared, which is going to be 1 over x.
No, I didn't understand.
Yeah.
So you multiply from the left and the right.
Yes, this is the average payoff that you're going to receive for the entire population.
You should get 100.
Sorry, you're right. I'm going to receive just one number here, which is 2x squared. But when you only multiply like this, so okay, so the idea is that you're looking at the average payoff that you're going to receive across your interactions, right? If you're going to look at the average payoff, so one time you'll be matched with me, and I'm playing, you're playing this, I'm playing here, okay? And sometimes you're going to meet C, but it has a different way of life.
So I always, if I'm the column player, I always
play this. Yes,
What is X in your multiplication?
X is the share of people who are using this strategy.
In the population.
In the population.
Whatever. Okay.
Exactly.
So
Why it's 1 minus 6.
So you multiply this, you'll get 2x, which is the average payoff if you only use this strategy, for the population that uses this strategy. But then you need to multiply it against the rest of the population, and you get the average for the entire population, which is
No, this is not the replicators.
it's the biologists think about. So if you go to Ofbar's book, they have 2 replicator dynamics, and one of them is this. Have this type of representation. I'm using this one just because the other one is going to be much more complex than analytically. And in the beginning, I started analytically, and I moved to a geometric picture.
Just multiply by the V.
Bye bye.
The V on the right hand side.
You multiply by the denominator.
It moves up.
Yes. No, so the ratio that usually appears, for example, their work and also in work that we have now with development is this type of implementation.
So this is the expected payoff in one state, yes?
for many interactions across the population at this time. Exactly, at this time.
Okay, and how it's so much dynamics, so how it's
Because actually you're going to combine here. State, this is this is the payoff that we're going to receive. If your a payoff compared to the rest of the population is greater than 1, you're going to grow. Otherwise, you're going to diminish. Okay.
Above average would be-
Above average, you get grow and share. Exactly. This is your own place. This is your goal.
let's see there is X prime is actually extra transpose.
Yes, X prime is the notation for X prime.
Be proportional to xj, which is not the case in the right hand side.
So would it be proportional?
Yeah.
So okay.
The question in the middle is proportional to fj, but not the one.
So what you will have in state 1, I'm just writing what you will have in state 1. So state 0, what they call state 0. So in state 0, this will be 2x, it will be 2x squared, it will be 1 over x minus 1. When you multiply it by x, it will be 1 minus minus x, it's the written here, x. That j used to be my s, so this is where the
Isn't j
comes from.
isn't j the strategy?
No. There is a mixture of notation here. So think of j as x. Okay, so in a sense, it would be what you're going to have. So the strategies are as follows. You play this. The share of the population, we're playing this strategy, right? This strategy here, also this strategy here, are x. Okay, and what's written here? Just ignore this j. State s. This is the equation. This is the type. Also this.
So this is the equation for the first strategy.
Yes. Okay. Exactly. The equation for x. X is the proportion of those playing the first strategy. Now obviously you can solve these equations. Okay, if I'm going to plot what is going to happen, then in the first state, state 0, what's
Derivative is 1.
yeah, so
When you start at 0.
exactly, so you converge to 1, right? So you converge to 1, so this is what will happen. So you'll start, say, from a certain point.
Stop when you get to.
Yeah, stop when you get to 1, but you will not stop, right? You will forever climb towards 1. So you're going to climb towards 1. But then at a certain instant, the state changes. And wherever you were, it could be that you were here or you were here. It starts exactly.
No, I mean at 0 it starts at the other. At 0, the derivative is 1, right?
It's 0. So
When x is 0, the
when x is 0, it stays 0, not when x is 0. It stays 0.
at state 0, when x is 0, you can see on the right.
It's 1 minus x, so it's positive, right? So you're going to grow towards 1, but gradually the derivative diminishes. It's going to look like this. So if this is your exactly. So what happens is that you're going to converge towards
Not
1.
concave,
Towards
not concave, concave.
yes, right. Sorry.
The question is incorrect because the solution is exponential. It goes outside of the input.
No. It's
The solution of xj dot xj is exponential.
what happens is that the closer you are to 1, you slow down. At the bottom, yes, but you're starting from a different point, right? And the other thing that we need to process.
Start x equals x.
Yeah, just 1 second. It will be that there should be a minus here. Yeah, there should be a minus. Yeah, there should be a minus. Should be a minus. Yeah. So I'll write it down. The other equation should look like this. Yes, you're right. There should be a minus there. There should be a minus.
But then it's not symmetric. It should be a minus plus one.
No, it's not a minus.
It should be symmetric.
No.
They're not supposed to add up to one.
It's following. The first, when you look at here, that's your growth rate. The two, this is where you're going to grow. You're going to grow towards one. So you're going to move from wherever you were towards point one. And then at a certain point, certain instant, you're going to switch to the other direction. Right? You're going to switch to the other direction. It's exactly Igor's observation. It should have been a minus there. And here you're going to move towards here. And then at a certain other instant, you're going to be here and you're going to start moving to the right because the state changed again, and so on and so forth.
This is stochastic based on the gamma.
Yes, exactly. Exactly. Switches are stochastic based on the gamma. And now, the main point behind the exponential convergence that you're going to have here is as follows. You're going to get very, very, very quickly to the other side. From wherever you were, you're going to get very, very, very quickly. So, for example, if we have around one, we take a certain interval here. Quite quickly, you're going to visit this interval. Well, depending on the gamma, if the gamma is very, very large, if we have, sorry, not large, very small, if you are going to have very, very slow rate of change, then with high probability, you're going to be very, very near one, right? And the same for the other direction. Very quickly, you're going to get, if the state is one, very, very quickly, you're going to get very, very, very close to the neighborhood of zero. So if you look at the amount of time that you're spending around every point, so for state zero, you're going to, if you're looking at the time, let's right now describe here the time that we're going to spend around each point. Most of the time is going to be spent here, right? And on the other way around, for state S equals 1, most of the time is going to be spent here. So it means that this ratio between this is just some technical thing. I mean, if I think that this gamma, the race, the norm of this goes to 0, both of them go to 0, and the ratio of them go to a certain alpha, then you're going to have a stationary distribution when gamma goes to infinity. The stationary distribution is going to be at state 0, going to be around, sorry, it shouldn't be 1 here, to be the other way around. So state 0 is going to be around 1, and in state 1 it's going to be around 0, and this is the proportion of time that you're going to spend around each one.
So what is alpha and this?
Right. So I'll
this is gamma is.
Right. So gamma is lambda. Yeah? Gamma is lambda. It's the amount of time. So 1 over gamma is the average amount of time that you spend in each state. Right? This is the average amount of time you spend in each state. And alpha, what we assume is that as they go to 0, dissolving times, assume that there is a certain proportion in these times. Shouldn't that be equal to 1? What?
Gamma 0, 1 divided by
1, 0. So lots of time for that. So if I look at the times that they spend at time 0 until I move to 1, there is going to be a certain proportion, or almost proportion, right? When they go to 0, between these two. So under this assumption, if there is such a limit, otherwise I will not have a certain limit for the stationary distribution. I have something that that may have certain fluctuation. But if this is correct, the ratio between them when they diminish to 0 goes to a certain alpha, then I'm going to be 1 over 1 plus alpha of the time around x equals 1 in this case, we do 0 to the other way around, and alpha over 1 plus alpha of the time going to be around x equals 0. And this is how the stationary distribution is going to look like when I take a gamma to 0 in such.
We're talking about two states, and alpha is the ratio of time between spent in that state.
In that state to the other state, exactly.
And you take the limits out of nowhere. You didn't talk about limits.
The gammas are the transition.
The transition property. And now what I'm saying, so before you can talk about this kind, we're going to look at that. If not, sorry, we're going to look, or it's now I'm going to say that we're going to look at what happens when you are allowed to stay a lot of time in state.
Okay, but is it true that alpha is the ratio between time spent here and time spent there?
For very, very long time that we spend in each state. If I'm in the situation where I stay very, very long time in summer, so the length of summer is 50% of the length of winter here in England. Yes? So again, the other way around. Winter is 10% of summer. We have not a very short winter. If you experience that as a period. And in that case, I think it's a reasonable setting the conditions. Then we are going to get this result. So the result is that the stationary, if you denote by pi gamma, the stationary exists such a stationary distribution when you have transitions down, then this is going to converge to pi, which is 1 over 1 plus alpha delta when s is 0, x is 1, plus alpha over 1 plus alpha delta. This is the argument that we had before. S is 1, x, when s is 1, you converge it to 0. When s is 0, you're converging to x equals 1.
So a very small number.
Yes. For a very, very, very small gamma. And this is going to happen in probability. Right? And, in this case, you can say more than that. But the convergence, not continuous convergence. In probability. So when you're looking at the this stationary distribution,
The limit.
this is the limit. Limit as gamma goes to 0. So there are occasions
Limit
where
of stationary distribution.
so there are occasions, obviously, when this gamma goes to 0, where you're going to so obviously there are occasions where when you change when this state when they change, it doesn't happen after a very, very long time.
This is convergence of measures, not of random variables. This cannot be converted, but it must be converted with conversion.
So if you have
the convergence of the stationary distribution.
Of a stationary distribution, yes. However, when for each, okay, we agree that for each gamma, we have we have a stationary distribution. The stationary distribution, is a certain distribution over paths, right? We have certain paths. With each state, we're going to have a certain mass that is for each.
That's what it says there. Distribution over these points.
Yes, so you're going to, there are going to be certain parts of the dynamics on which you're not going to converge to this type.
So what is the stationary distributions converge?
The stationary distributions, they converge to another
So the
distribution.
stationary converge.
Yes, their convergence is a weak convergence in the sense of. However, sometimes you will not have this type of convergence, right? There are certain paths that are not going to converge.
But we are talking about the convergence of stationary distributions, not of pairs. Or what are we talking about?
Let's write down.
Then for each gamma, there's a stationary distribution, and you look at the path of the stationary distribution.
Exactly. So to be what you're calling weak convergence is the same thing.
What is the
I think that's good. I'll write it down. So it could be it's taken here. So so you have a pi of gamma, and
which is a probability distribution of a risk from itself.
which is the probability distribution. Yes, so the probability distribution pi gamma is the probability distribution. I just write it down here so we can see it. It's a probability distribution, and I think that maybe right, and I was confusing certain notions. For each gamma, we have such a creature, and as gamma goes to 0, so yes, it could be that I'm mixing here, and should have written weak. One second. So. Yes. What you want to show is that, in a sense, when I'm looking at every continuous function that is concentrated around either 0 or 1, then this doesn't vanish. The average of this doesn't vanish, but when you're between them, so you may be wrong. You may be wrong. Maybe this is what I'm correct myself there on this error throughout.
No.
No?
The convergence is the measure of it.
No. It's the integral. Yeah, it's the integral d. Right? It's the integral d. And what we actually had proven is that when f is supported around a 0 or 1, then this is not 0, and when it's not supported there, then you're actually going to get in the limit, you're going to get I think Figel is right, probably as usual. This is what we actually have.
What should we take from this example?
So okay, so this is what I'm going to so this example was just building the intuition. The intuition is that in some sense, in these examples or in examples where you're going to have equilibrium, you're going to converge up to a certain time to a certain point, and when when you switch to the other state, you're going to move to another processes.
We can
If the process is we cannot that's not we can. But
all the reach.
the only thing that we reach is that in a finite time, in a certain finite time, you're going to hit every small ball around the equilibrium, either x equals 0 or x equals 1. And then if lambda gamma is small enough, then once you hit that place, most of the time it's going to be spent around either x equals 1 or x equals 0.
The issue is not, the issue is that, as I understand, it's not gamma, but the proportion between gamma and the
This is
speed of
also-
the convergence.
Yes, and this is also important. But if you don't have that, there's not going to have fluctuations here. And you cannot expect to have to spend, for example, 50% of the time here.
Yeah, of course, it depends on the speed of the convergence and the number of switches.
Exactly.
So this is the degenerate example, right? We have two states.
Yeah, exactly. It's for the very, very beginning.
They are separated in a sense.
They are separated. And in a sense, this is going to be the flavor of the name.
Why wouldn't you change just the speed of the differential equation? A single parameter.
So the speed of
the Nish probability stay constant, but the differential equation gets forward, gets system.
gets faster. So even in this example, I think that the differential equation is in this case it gets slower and slower.
Just multiply the right hand side by c, and let's see.
So yeah, it's so if we multiply this side by a certain c, and this side by okay, so this side by c, and c becomes larger and larger. How does that?
You get it one time.
That's effectively
Same effect, if you keep gamma
Yes.
at some value and make it faster, the convergence.
What you have in that? It's only a question. How measure time? Instead of making gammas a change, you make a change in time frame. Yes. So you can effectively divide the time by gamma with the derivative. Right. It's a good way to present. Okay, so now example 1, 2. Example 1, 2 is called 1, 2 because before we had 1, 1. 1, 1 meant that we have in one state we have one equilibrium, the other state one ESS, and the other case we have one ESS. Now we're going to have in one state 2 ESS, in the other state 1 ESS. This is 1. Okay. Now let's see what's going to happen here. So in this state, we're going to have this is an ESS 2/3, right? X is going to be 2/3. Calculate that. And here we're going to have two options. Either we're going to, for a certain point, we're going to converge to here, and from we're left to a certain threshold, we're going to converge here.
That's x1. X1.
Yeah.
But it's the mixed equilibrium and it's not better.
No, in this stage, that's the only stable. In a sense, you're going to have the maximum is going to be here.
It's not, okay,
Exactly.
I confused the.
Exactly.
The
And
actions.
here, in some sense,
The goals.
the graph that you're going to have is like that. You're going to get
Games is state, yeah.
the game, yeah. Yeah, so each state has a game, right? Each state has a game. And so, in a sense, this is the picture. We're going to have equilibrium here at the end, and here at 2/3, we're going to have this. We're going to have a purple state, and I think the whiteboard I will be able to explain it to you here. So let's try and do the same thing here, but just geometry. Just geometry. So suppose that I start here. This is the attraction threshold. So if I the left of this line, I'm going to be attracted here, I'm going to be attracted towards 0, and the right hand side is going to be attracted.
This point is 1/3, right?
Which point? There?
The attraction and threshold.
In this case, I think. So you're going to be attracted to this direction, right? And at a certain time, you're going to switch between states 0 and 1. So you're going to stay here at this point, where at this x, which is very, very close to 1 in this case. And you're going to move here. And then you're going to move towards this equilibrium here. And then after a long period, you're going to do the same thing here. And if the time is sufficiently long, then you're going to be sufficiently close to this. Exactly. And then you're going to push to the right. And essentially, what we're going to have support. Like this. This is going to be the support. In this case, we're going to be here. In this case, we're going to be here. This thing is going to disappear. So if you recall the game that we had, we are going to eliminate x. In this case, x is 1 or equals 0. So
some depends on the threshold.
yes, there is a dependence on the threshold. It's very, very important. It's very important. If the threshold, so for example, this is correct because if the threshold is exactly where this equilibrium is, then if we start from the right, we're going to get one outcome. If we start from the left, we're going to get a different outcome. Okay, but generically, if you look generically at the initial conditions, then and you're going to converge to a very, very specific thing that essentially eliminates exactly and eliminates one of the equilibria in one. So the 1 becomes a 1.
So which one is the eliminate?
This one is eliminated because eventually you're going to be here that once you transition. Yeah. Once you transition, when you're sufficiently near here, you're going to be moved into here, and then this is going to be the output.
Oh, if the threshold is on the other side, you get the other way.
Yeah, if the threshold is on the other side, we're going to take that one. Right. Exactly. If it's exactly on the purple, you're actually going to have two cases.
The initial state.
The initial state is going to determine a lot. Exactly. But generically, the state doesn't.
And then the other one is
The third again. Okay. Okay. So time longer than I expected to do this. Mainly because of me.
But we enjoy.
Enjoy that.
the path is more important.
I struggled on there some things on the other actually. We converge to a better prediction.
The most often held sentence ever.
Yeah, obviously, especially when you present it the first time, and it's just in its diapers, right? And it's still okay. So I'm going to use a finite set of states of nature, S. This is going to be my state. And typically, whatever I'm going to present is going to be 0 or 1. It's finite, 0 or 1. That's the smallest meaningful example. And we're going to have population states that are going to be delta over n. You're going to have n strategies. Right? In this game, symmetric game, person symmetric game. In the dynamics, so here once again, I denote the J as my state, not S. They're going to follow a Markov jump process. Okay. And the population states, so I'm going to have states of nature, and I'm going to have population states. The X are a population state, and the S are states of nature. And for each J, fine. For each J between 1 and n, I'm going to have, depending on the state, I'm going to have a certain replicator dynamics. And here, A is a matrix that depends also on S. Right? It's going to depend also on S.
I don't like this for you.
Okay.
We have like the computer scientists, you assume that the denominator is always positive.
Yes, you're right. In some sense, I'm assuming that I can put upwards.
This is not a quarter you like.
So for example, actually came from biology. In biology, there is a usual assumption in many works, also in works of Edhan, that there is some population sometimes will disappear, or in terms of the average doesn't disappear.
Just multiply by the denominator over this.
Yes.
Many of those models, they also assume the payoff is positive. It's often between 0 and 1.
Yeah.
But they can always have a affine transformation.
Yeah.
And get the same path. So they just affine transform the model.
But I think essentially that if you multiply by the denominator, it's all one that we're used to and so on and so forth. And eventually, but it's true, I think, for stability analysis, because then you can put it out of the matrix and all the usual analysis. When it comes to phase space, yes, I can probably do the same thing with the order replicator. And also, I demand that the path for the x's for the proportional population are going to be continuous. This is what I'm going to do. I'm going to ask if it's going to be continuous. There is not so when temperature change or summer rise, the population doesn't grow or diminish because of that.
What is the notation?
So the strategy J.
The tau.
Where?
Left limit.
The left limit. The left limit. So when you have an arrival at tau, when you're a little bit below tau, that's before the jump, right? And the tau you already jumped. X is going to be the same.
That's the left limit, and you denote it by
Minus.
this on the right.
Why do we need the?
Right,
It's on the right.
This is like that.
Okay.
yes.
Why do we?
No, the solution are
That process, you need to
it could be, you can make an assumption that people may do that. For example, part of the process is that we have some sort of an extinction event. Every time tau arrives, we have an extinction event, very local at this time, and then the population. I want to eliminate them.
Now the Markov jump replaces the gamma from before.
Yeah. So also before it was a market. And I'm going to call it simple because in my interpretation, the transitions of F are independent from the frequency X.
Endogenous.
It's exogenous. It's an exogenous chain, right? So in some sense, it's more similar to a summer or the winter, or for a change in regulations, and less to something that happens, for example, a crisis that comes because we invested too much in the asset. Right? So you can think of a model, think about it later, but because we invest more in a risky asset, the probability for a certain crisis will increase. This is not a model. Okay. So once again, I'd like to study stationary distribution.
What is long holding time?
Holding time is exactly the next bullet. That these gammas, the transition matrix that we're going to have in this case, very simple matrix. The norm is going to diminish to zero. Okay, so this is long holding times, and the assumption that I'm going to make is the same assumption as I had before. If the stationary distribution of this Markov jump process is theta of gamma, and then as gamma goes to 0, it's going to converge to a certain distribution theta. Right? So before this theta was the 1 over 1 plus alpha and the alpha over 1 plus alpha.
We have sufficient conditions for that?
No, I don't have sufficient conditions for that. This is one of the things that I'm interested in. I'll talk about all the things that already discovered, some things that I need to change, but there are lots of things that I'm still looking at, and this is one of them. And then there is also the question of existence of, okay, fine, I can show you the existence of one, but it's unique, for example. Right? It's not completely clear that uniqueness necessarily follows from what I showed you so far. At least to me. Happy to. So the second assumption is there is a stationary distribution. So, and then I'm going to, yeah, and then I'm going to try and calculate. And the objective, as before, is to study this stationary distribution or how it behaves as this gamma, as the holding time solution. We spend more and more time in each.
The previous example, if gamma wasn't so slow, I mean the switches were not, the rate of switches was even faster.
Yes, okay, yeah.
Still, you could say that the stationary probability, the stationary distribution will be between only two equilibria, right?
Yes, but in a sense, the stationary is not between two equilibrium, but you're still going to spend some time in the middle.
But not on the left. You could eliminate in the previous slide.
Yeah.
You could eliminate the left, even if gamma wasn't so. Even if the switches were very slow at some point, you would be behind the threshold, right?
Yes,
At some point,
most
from there
of the paths. Yes, we are proportional.
at some point, even if the switches are very quick, but random, at some point you will be on the right of the threshold of the red line.
At some point.
At some point, and you will switch to one. And from that point
So
of time,
okay.
you will be on the right side of the line.
So that point, only if you switch from nine series. What we need is, and you're right, there will be a positive probability. Exactly, there will be a positive probability.
What I want to say is that in the limit, you don't care about the rate of switching. If
You
you
just
are
care about drifted, and there is a positive probability that will be drifting into here, and then
that's all.
and that's it.
In the limit,
You can get a sample 1.3 by again fixing the gamma and just speeding the definition.
Okay. Better approach. But what Amnon says is that we don't need that. We can.
we don't.
In a sense, in this example, just because you're drifting in all kinds of direction, there is a positive probability that you're going to arrive here, and at that point switch, and that's it.
That's all.
You're going
From
to
there,
stay.
you're
You're going to have to be carried here. So
I don't care about the rate of switching.
Yeah.
All the
So we understand the support of this
Fraction states.
That's right. You can, no, that is what I want to say.
it's there. Will not be carried.
What you can say, we are not gonna be in the in around this equilibria. I would like to say when is a situation that you can eliminate all the range on the left of the threshold. That's
So
all.
in a sense,
This is going to disappear. It doesn't mean that you will be around very close to the
we think that we will pass this point many times. I agree. Okay, so so in a sense, if you want to understand two by two games, then the last picture that I need to describe is something like this, right? This is the last picture that I need to describe for two by two games, and later on I'll say something about more general picture and the problems that we're going to have to push forward.
Can it be this 3 point?
Right. No, it's not 3 points, it's the initial point. Right. I agree. I don't know, the only that case is 2-2, right? In my
And you have two thresholds.
yeah, exactly. You're going to have a threshold here and a threshold here, and the black points are the dynamics. Black points are the dynamics, the colors are the states, and this is the equilibria here and here. equilibria here.
You have a purple threshold and a red threshold.
So now we can play all around.
Yeah, exactly. And now what happens with sufficiently high probability you're going to move here. And as you said, this also is true here because you're moving in this direction. With some probability, I'm going to be pushed above this threshold. And then when I move, I will move here and I'll be able to eliminate the right hand side. Okay, but in my setting, with sufficiently high probability, you're going to move and towards this threshold, and then this is going to be the support where when you take the limit, and in a sense, and the idea is that if you start from the right of this threshold, you're going to be carried in. So even though we have many equilibria here,
So the initial point determines.
No, but again, it determines with high probability, not with the probability one, right? Because I may switch down. I may switch down immediately.
exactly. And so here, what happens is that we may switch down immediately. So it's going to happen with so instead, even here, this is going to have a low probability. So we start from here. This thing happens with a low probability. If we move, if our initial x is here, this is going to happen with high probability, and this is going to happen.
On the right, on the right of the threshold, it's also will go back.
Exactly. It's on the right, yeah, exactly. If it's on the right of this threshold, and also, for example, if you would have started here
On the left of the threshold.
So this is the characterization. Okay. So now I'm going to talk about m larger than 2. Take m equal 3, right? I'm going to describe some geometric issues that are going to prevent us from having the previous picture. And once again, we're going to have only 2 states. And we're going to have a pattern that looks like that. State 0, suppose that you have a certain equilibrium, which is a sink. Right? It's going to have this type of spiral convergence into it. And suppose that when you look at the attractors or stable manifolds at state 1, they're going to look like that. There is going to be a low dimensional stable manifold that passes through our equilibrium, passes through every small ball around the equilibrium. And then you're going to have 2 other stable manifolds that are based around it.
I'm sorry, I missed. So what is this lines? What are these?
So these lines have a replicator dynamics. Replicator dynamics in
Each
Right,
point
yeah,
is what? Is the proportion?
once again,
The x and the y?
in this case, we are looking, I'm actually looking, it's not equal y, this is the simplex. So when you look at the 3-dimensional simplex, it's the y, right? So one on the whiteboard converge in such a way into a certain. And then
What is a sink?
sink is something that looks like the water when they're going down the sink. It's an attracting point that in some sense it looks like a spiral. Spiraling.
Is a sink simply an attracting point or the?
Yes, it's an attracting point plus this condition that when you take a line here, it passes through it infinitely many times.
Nice.
Okay.
That's what we really difference.
So before we had certain thresholds, right? From the right of the threshold, left of the threshold. Suppose that now we have a threshold for the second state, state 1. It could be that one of them passes right through here, right? And then, I don't know, it has an equilibrium, say, somewhere here. And you have other two that are really right next to it. Right? You see a little bit, you're in another basin of attraction. And this basin of attraction here is going to attract you to a certain equilibrium here. And this basin of attraction, this large set that you're going to have here, is going to attract you to a certain equilibrium here.
A mixed equilibrium?
Yeah, it could be on the this equilibrium on the boundary of the sequence. Okay, so this is what can happen. You have a mix between 1 and 2 and 1 and 3, and something is going to pass in the middle, right? This is what you're going to have there. And in this type of thing, what happens? So suppose that we're following Amnon's suggestion. At a certain time, I'm going to be here with great probability, and then I'm going to be attracted to the equilibrium that we have here. But on the other way around, same holds true here. And how it can be here? There is no way to decide. But perhaps there is a way to decide.
How did you probability to visit each one of them?
Yeah, but if you're going to try and factorize the limits, then it's extremely difficult.
But you know that it's possible.
Yeah, I know that. Perhaps they can do that. But they don't want to be different, right? Because you're going to try and sell it. It's complex. Right? But happily enough, if I perturb things a little bit, then this line is going to move away from this. Right?
So that one is measured zero.
Yeah, exactly. It's even more than measure zero. It's
More than zero. I mean, this.
Generically, if I just check you a little bit, you're going to lose this type of thing. This picture is going to change, right? So,
What happens?
so I'm going to, yeah, I think that this should go. I'll return to this slide. So I'm going to consider Morse gain systems. Morse gain systems are going to be the following thing. This is the result I'm going to describe. In a second, I'm going to describe it with a picture. Okay. But it's exactly the same idea. There is a replicator there. Forget about the fields. There is something that we will call it a Morse gain. Morse gain means that I can describe the simplex as the union over the stable equilibria for the stable sets of X. The stable set of X, just to for those who don't know that, is the following thing. What are the W's? I'm just going to explain this definition, and I'm going to show you the ABN result. So you have a certain equilibrium, and you can think of all the points such that when times go to infinity, you're going to move and converge eventually to this equilibrium. So this is called the stable set of this equilibrium.
It's not the basin of attraction.
No, I think that what the people think of as a basin of attraction is a slightly different set, which is usually an open set.
Okay, so again, the definition of W star is
W star is all the points where all the initial conditions, such that at infinite time, call it the basin of attraction, you're going to converge to this equilibrium.
So now you partition the space.
Yeah, it partitions the space plus a certain set n, which was the very thin line that we had before. Right, so I'm going to have these very chunky sets from which I converge to very stable. And I have these very, very thin lines of which, well, eventually I will not care about.
And it's called the separators.
Separators.
Well, could you please say again what's the difference between the stable set of X star and the basin of attraction?
That's the question of
Yeah, I didn't get the answer.
I think that the way it's used is that usually the basin of attraction should be an open set or something like that. So I'm not really in here, so I need to check exactly what's the
But
difference.
conceptually, that's the difference.
Yes, conceptually, that's the conceptually that yeah, it's just not necessarily an open set. Just 1 second. Yeah. So n is going to be a lower that's going to be some manifold of a lower dimension or something. And on top of that, I'm going to say that it's a more system. More system is when the ESS at state S don't intersect the set n that we have.
It's not more like this.
What?
It's a line, then it's not more like this.
No,
I always it.
it is. It is in a higher dimension,
Okay,
It is.
I'm sorry.
right? It's that's exactly generic, right? The idea of generic set.
Classic example, no.
Exactly. Exactly. Okay. So so if you take
You think you know ESS on the normal.
yes, exactly. The ESS don't intersect like this. So where does it lead to? So just an example. If you take Morse games, an example of Morse games are potential games, right? And if you also add to it the Morse system assumption, then we have an example. Another example, generic example, are 3x3 games. Nothing. All right, so let's have a look at what we have. We're just going to do it in 2 dimensions. So I'm going to consider equilibrium cycles here. So suppose that we start somewhere near this red equilibrium. Think of it as a ball around this equilibrium. And by the assumption that we have, we're going to have for this purple equilibrium, we're going to have a stable manifold that is going to have be this very chunky manifold, and it's going to contain this. In this example, it's going to contain this equilibrium, this red equilibrium. So if you converge toward this red equilibrium, eventually you're going to enter this purple set. And if the state changes when you're in the set, then what's going to happen? You're going to start moving towards this equilibrium here. And now, when you are near this equilibrium here, you need to ask yourself, in which set am I going to find myself? I'm going to find myself in a set that has a certain a red set, right? Which converges at every point it converges towards this red equilibrium. And then again, we're going to have the same picture for this equilibrium here. And eventually, we're going to, after many times, there's going to be a certain point that we're going to close the cycle. Okay. And here's another. So this is the way we're going to move is from top left to bottom left to bottom right to top right, and then
You're assuming this cycle exists.
so a cycle is going to exist because of its
Same cycle always, this is the result.
yeah, this is the result. The cycle will exist generically. Another example is this, right? So we start from this equilibrium. This equilibrium is within the stable manifold, this purple equilibrium here. We start sliding towards this, but now for this equilibrium, it's within the stable manifold of this red equilibrium here, right? So what will happen? This is going to be the cycle. Cycle is going to be this, right? And as you said, generically, we're going to have generically we're going to have a cycle. Such a cycle because of the assumption that we have, because you're going to move from one to another, right? You have only finitely many of them. Actually, you're going to run into one you already do.
It's not immediate.
What is the limit stationary distribution?
Just a second. Right, where is the stationary distribution? The limit in the limit stationary distribution. It's going to be essentially the following thing. Let's take this one here. So you're going to visit. You're going to stay around this point for a certain amount of time, most of the time. right? Not exactly most of the time. It's going to be the time that we're going to stay around it is the essentially proportional to the time that you spend at state 0, right? And then you're going to move to this state. So conditionally on being in this state, you're going to spend here the proportional time is going to be proportional to the time that you spend in this state. But you have 2K of them. You have 4 of them. So here, this one you're going to spend half of the time, right? The time is going to be split half here and half here.
That depends on the transition.
No, transition probability only depends how much time you're going to stay at state 0 and at state 1, right? This is what you're going to do, but
What is the regardless of the transition probability?
it's going to depend only on this cycle. Because it's not going to be half, it's going to be half up between this and this.
Right.
So it's going to be half of the time that. So in total for this point,
Is it obviously going to be half?
just
It's independent.
yes, it's independent. Yes.
Okay.
I don't know if it's obvious.
Oh, why do we have all these cycles? Why don't we have extinction?
Why don't you? Because you. Okay, so there is no noise here, right? I mean, it's continuous time variable, and also in all ways, you're going to have an x. All the x's are going to be positive, right? You start from generically. You start from a random x. Okay. All the coordinates are going to be positive, and because it's a replicator dynamics, you don't convert to the boundaries of finite time. You don't converge to anything, any equilibrium point in a finite time.
You say that's true for replicator.
For replicator dynamics, it's not true, for example, for stochastic replicator dynamics. So if you add noise here, depends on the way you add the noise, you may converge in finite time to the boundaries. It's a paper based on Young and Foster that has this 1991. Okay. So another example on top of potential gains are 3x3 gains. So 3x3 gains generically, 3x3 gains, they may have a limit cycle. They may have something that moves in a cycle, okay, like I wrote at the city. If you shake it a little bit, you are left with this type of equilibria that you can move between them. And if you have a more system structure, then we can cover also this type of family of games. It will not work for n larger. Because for n larger equal to 4, it seems that there are results, very old results, that show that if you shake the game a little bit, you don't get rid of limit cycles. You also have a chaotic behavior that appears and actually quite stable. If I shake the game a little bit, question is, can I take the picture that I had before, this picture that I have here, right, and push it towards other type of limit sets, but the limit sets are not points? I don't know. That's essentially the end of my talk. I can tell you what are the things that are much less certain of. Probably need some further study. Most of them, I think. Example, the station is especially here. I think so.
The non-generic case can be interesting. So, for example, when it spirals,
Yes.
and then depending on whether it's on the right or the left of the plane, so perhaps there's a limit to the proportion of time.
Yeah, and under certain conditions, you can prove that. So for example, I can essentially tell you exactly what the conditions are. So very close to tell you what the conditions are. So suppose that you look at this type of thing, and you look at the time for every time t, very large time t, you look exactly at what you said, the time that you spend on the right, the time that you spend on the left. If it has a limit, then you'll be able to characterize it.
Right.
Okay, but it may have fluctuations.
Yeah.
It may have fluctuations. That's the main problem. But in a sense, it's very similar to my assumption on the ratios of the gas, right? If you have this type of in some sense the empirical measure or something like that you spend. It depends on the.
You look at the solution.
Yeah, look at the solution and look at the time that it spends on the right, the time it spends on the left, right? And then you need that for when you take the limit over t, right? Eventually it's going to get into a certain smaller and smaller and smaller areas. When you take this limit on size of the ball that you're looking at, something like that, you need this thing to converge.
And do you know whether you converge or something?
No, we don't. That's one.
That's quite simple. You have an explicit solution for that.
Yeah. Don't know. Didn't check. I know that if I have a universal, so it's true that you have an explicit solution, for example, in certain cases, of the general case. Don't know to say something general. For a specific thing,
Omer, I apologize. I need a summary about many results.
Okay. So the main, so in some sense, this is the main result or idea that we're going to have cycles, equilibrium cycles. What we're going to get are equilibrium cycles that we're going to
From two states.
For any number of states, for example, as long as you have this structure that they talked about of Morse gains. And Morse gains, for example, are covered by potential gains, but also generically by 3x3 gains. Okay. And as long as you have this structure, it doesn't matter what the gain is, as long as you have this type of structure that you're only going to have, essentially you're going to have only equilibrium in the dynamic set. And so the stable sets of states of this game are not going to be linked cycles, not going to be some strange attractors or whatever, they're going to be equilibrium. And you're going to have this type of behavior of motion between those equilibria, and all the other equilibria are going to disappear.
So depend on the states.
Depends on where you started from, exactly where you start from, you reach a condition, it's going to determine a certain cycle, and it's going to map into a certain cycle generically.
Yeah, but what I don't understand is you could define the dynamics of the two states differently, and then you would not have the cycle, right? I mean, the dynamics in each state, you decide what is the dynamic.
No, okay, right. So if you have, as long as you have slide like this, and for example, this is a Morse gain system, and you have it for potential gains with the replicator dynamics. So if the dynamics is the replicator dynamics, and you have a potential gain, it will hold. If it's not the replicator dynamics, then perhaps, as I said, I have a bullet for that, perhaps for different types of dynamics, I still don't know what to say there. I have some suspicions about best response, for example. But I don't know what to say about other dynamics. But for the replicator dynamics, this thing holds. Right? This thing is also the replicator dynamics. And so as long as you have this structure, there are examples for dynamics that actually replicator dynamics is an important example. Okay, then you're going to have a cycle. Cycles, and it's going to eliminate a lot of the equilibrium. So this type of shifting between so the initial result that we had some will disappear. You can maintain.
What applications is there? Like a traffic congestion game with the training of the
Right, this is the point for discussion. I have some things in mind. Things that I had in mind are So more examples, right? So for example, yes, and this remain could be, again, I don't have to, the main result that I had in mind is on growth, right? So that's the example that I actually have in my mind is it's temporary equilibrium. GDP growth? Yes, for example, from a certain gain that leads to a certain growth, and usually we ask ourselves what type of equilibrium can we select. So I tell you, okay, there's going to be a certain path of equilibrium that we're going to move between, and that's it. You shouldn't care about the risk.
So it's so it's switching between vectors of populations, right?
Yes, exactly. You
All these
exactly. You move and you move between different for each state, you're going to have this equilibrium now, and then you're going to slide into the other equilibrium when it switches, and then you slide into another equilibrium, which may not be the initial equilibrium that you have, but eventually you're going to go back to it, and you're going to move between them, and all the other equilibria that you ever have immaterial. This is the main point of it. Of this. And yes, there are lots of things that Edhan mentioned. What happens when not talking about this generic case? This is also, I know, this is the only argument that I can say in general. Particularly, yes, perhaps I can do some calculation for a specific example. Not very optimistic of what I can do in general in that case. So, for example, other changing environment. I have just 1 minute. I'll pick one of these, or perhaps you want to pick one of these, and tell me what is the most interesting for you. What is interesting for Amnon? Amnon, which is the dictator. I don't know. Pick for us. You know. Okay. So I'll take the other changing environment. It's because Gilad mentioned it early on. So for example, up until now, a lot of the things that I said depend on switching randomly between finitely many states. But for example, one typical question is that, okay, perhaps you have some direction, there's a gradual change, you get something completely different. Another point that may harm or change the result, if we add some noise, then I'm going to, in some models, I'm going to hit the boundary in finite time. Okay, if I hit the boundary in finite time, then you're right, there is some issue with this type of analysis. And one example is a gradual, I think, gradual climate change or gradual change in a certain regime, right? And here you have a motion between essentially parameter of the gain change gradually with a certain amount of noise, and that will be interesting to also look at. So there are lots of possibilities to consider.